Preface and Chapter 1 of The Study of Eclipses. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Awai in August 2017. The Story of Eclipses, simply told for general readers, with a special reference to the total eclipse of the Sun of May 28, 1900, by George F. Chambers, Fellow of the Royal Astronomical Society. Preface. The present volume is intended as a sequel to my two former volumes in the Nunes series of Useful Stories, entitled respectively The Story of the Solar System and The Story of the Stars. It has been written not only as a necessary complement, so to speak, to those works, but because public attention is already being directed to the forthcoming total eclipse of the Sun on May 28, 1900. This eclipse, though only visible as a partial one in England, will be total no further off than Portugal and Spain. Considering also that the line of totality will pass across a large tract of country forming part of the United States, it may be inferred that there will be an enormous number of English-speaking spectators of the phenomenon. It is for these in general that this little book has been written. For the guidance of those who may be expected to visit Portugal or Spain, a temporary appendix has been prepared, giving a large amount of information showing how those countries can be best reached, whether by sea or over land, from the shores of England. If anyone is inclined to doubt whether an eclipse expedition is likely to provide non-astronomical tourists with incidents of travel, pleasant, profitable, and even amusing, perhaps the doubt will be removed by a perusal of the accounts of Sir F. Galton's trip to Spain in 1860, Vacation Tourists in 1860, page 422, or of Professor Tyndall's trip to Algeria in 1870, Hours of Exercise in the Alps, page 429, or of Professor Langley's adventures on Pikes Peak in the Rocky Mountains, Colorado, U.S., in 1878. Washington Observations 1876, Appendix 3, page 203. Or of some of the many magazine and other narratives of the Norway eclipse of 1896 and the Indian eclipse of 1898. Subject to these special points, no further prefatory explanation seems needed, the general style of the contents being, mutatis mutandis, identical with the contents of the volumes which have gone before. I have to thank my friend, Dr. A. M. W. Downing, the superintendent of the Nautical Almanac, for kindly verifying the calculations in chapters 2 and 3. G.F.C. Northfield Grange, Eastbourne, 1899. Chapter 1. Introduction. It may, I fear, be taken as a truism that the man in the street, collectively the general public, knows little and cares less for what is called physical science. Now and again, when something remarkable happens, such as a great thunderstorm or an earthquake, or a volcanic eruption or a brilliant comet, or a total eclipse, something in fact which has become the talk of the town, our friend will condescend to give the matter the barest amount of attention, whilst he is filling his pipe or mixing a whisky and soda. But there is not in England that general attention given to the displays of nature and the philosophy of those displays, which certainly is a characteristic of the phlegmatic German. However, things are better than they used to be, and the forthcoming total eclipse of the Sun of May 28, 1900, visible as it will be as a partial eclipse all over Great Britain and Ireland, and as a total eclipse in countries so near to Great Britain as Spain and Portugal, to say nothing of the United States, will probably not only attract a good deal of attention on the part of many millions of English-speaking people, but may also be expected to induce a numerically respectable remnant to give their minds and thoughts, with a certain amount of patient attention, to the science and philosophy of eclipses. There are other causes likely to cooperate in bringing this about. It is true that men's minds are more enlightened at the end of the 19th century than they were at the end of the 16th century, and that a trip to Spain will awaken vastly different thoughts in the year 1900 to those which would have been awakened, say, in the year 1587. But for all that, a certain amount of superstition still lingers in the world, and total eclipses, as well as comets, still give rise to feelings of anxiety and alarm amongst ill-educated villagers, even in so-called civilized countries. Some amusing illustrations of this will be presented in due course. For the moment, let me content myself by stating the immediate aim of this little book, and the circumstances which have led to its being written. What those circumstances are will be understood generally from what has been said already. Its aim is the unambitious one of presenting in readable, yet sound scientific language, a popular account of eclipses of the sun and moon, and, very briefly, of certain kindred astronomical phenomena which depend upon causes in some degree similar to those which operate in connection with eclipses. These kindred phenomena are technically known as transits and occultations. Putting these two matters entirely aside for the present, we will confine our attention in the first instance to eclipses, and as eclipses of the sun do not stand quite on the same footing as eclipses of the moon, we will, after stating the general circumstances of the case, put the eclipses of the moon aside for a while. End of chapter 1.
Chapter 2 of the Story of Eclipses. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Linda Olson-Fytak, Los Angeles. The Story of Eclipses by George Chambers. Chapter 2. General Ideas. The primary meaning of the word eclipse, eclipsos, is a forsaking, quitting, or disappearance. Hence, the covering over of something by something else, or the immersion of something in something. And these apparently crude definitions will be found on investigation to represent precisely the facts of the case. Inasmuch as the earth and the moon are, for our present purpose, practically solid bodies, each must cast a shadow into space as the result of being illuminated by the sun, regarded as a source of light. What we shall eventually have to consider is, what results arise from the existence of these shadows according to the circumstances under which they are viewed. But before reaching this point, some other preliminary considerations must be dealt with. The various bodies which together make up the solar system, that is to say, in particular, those bodies called the planets, some of them primary, others secondary, alias satellites or moons, are constantly in motion. Consequently, if we imagine a line to be drawn between any two at any given time, such a line will point in a different direction at another time, and so it may occasionally happen that three of these ever-moving bodies will come into one and the same straight line. Now the consequences of this state of things were admirably well pointed out nearly half a century ago by a popular writer who in his day greatly aided the development of science amongst the masses. When one of the extremes of the series of three bodies which thus assume a common direction is the sun, the intermediate body deprives the other extreme body either wholly or partially of the illumination which it habitually receives. When one of the extremes is the Earth, the intermediate body intercepts wholly or partially the other extreme body from the view of the observers situated at places on the Earth which are in the common line of direction, and the intermediate body is seen to pass over the other extreme body as it enters upon or leaves the common line of direction. The phenomena resulting from such contingencies of position and direction are variously denominated eclipses, transits, and occultations according to the relative apparent magnitudes of the interposing and obscured bodies and according to the circumstances which attend them. The Earth moves around the Sun once in every year. The Moon moves around the Earth once in every lunar month, 27 days. I hope everybody understands those essential facts. Then we must note that the Earth moves round the Sun in a certain plane. It is nothing for our present purpose what that plane is. If the Moon, as the Earth's companion, moved round the Earth in the same plane, an eclipse of the Sun would happen regularly every month when the Moon was in conjunction, new moon, and also every month at the intermediate period there would be a total eclipse of the Moon on the occasion of every opposition or full moon. But inasmuch as the Moon's orbit does not lie in quite the same plane as the Earth's, but is inclined thereto at an angle which may be taken to average about 5 1/8 degrees, the actual facts are different. That is to say, instead of there being in every year about 25 eclipses, solar and lunar, in nearly equal numbers, which there would be if the orbits had identical planes, there are only a very few eclipses in the year, never, under the most favourable circumstances, more than 7, and sometimes as few as 2. Nor are the numbers equally apportioned. In years where there are 7 eclipses, 5 of them may be of the Sun and 2 of the Moon. Where there are only 2 eclipses, both must be of the Sun. Under no circumstances can there be in any one year more than 3 eclipses of the Moon, and in some years there will be none. The reasons for these diversities are of a technical character, and a full elucidation of them would not be of interest to the general reader. It may here be added parenthetically that the occasions will be very rare of there being 5 solar eclipses in one year. This last happened in 1823, and will only happen once again in the next 2 centuries, namely in 1935. If a total eclipse of the Sun happens early in January, there may be another in December of the same year, as in 1889, January 1st and December 22nd. This will not happen again till 2057, when there will be total eclipses on January 5th and December 26th. There is one very curious fact which may be here conveniently stated as a bare fact, reserving the explanation of it for a future page, namely, that eclipses of the Sun and Moon are linked together in a certain chain or sequence, which takes rather more than 18 years to run out when the sequence recurs and recurs ad infinitum. In this 18-year period, which bears the name of the Saros, there usually happen 70 eclipses, of which 41 are of the Sun and 29 of the Moon. Accordingly, eclipses of the Sun are more numerous than those of the Moon in the proportion of about 3 to 2. Yet at any given place on the Earth, more lunar eclipses are visible than solar eclipses, because the former, when they occur, are visible over the whole hemisphere of the Earth, which is turned towards the Moon, whilst the area over which a total eclipse of the Sun is visible is but a belt of the Earth no more than about 150 to 170 miles wide. Partial eclipses of the Sun, however, are visible over a very much wider area on either side of the path traversed by the Moon's shadow. Confining our attention in the first instance to eclipses of the Sun, the diagrams Figure 2 and Figure 3 will make clear, with very little verbal description, the essential features of the two principal kinds of eclipses of the Sun. In these figures, S represents the Sun, M the Moon, and E the Earth. They are not, of course, even approximately drawn to scale, either as to the size of the bodies or their relative distances, but this is a matter of no moment as regards the principles involved. M, being in sunshine, receives light on, as it were, the left-hand side, which faces S, the Sun. The shadow of the Moon cast into space is, in the particular case, thrown as regards its tip on to the Earth, and is intercepted by the Earth. Persons at the moment situated on the Earth within the limits of this shadow will not see any part of the Sun at all. They will see, in fact, nothing but the Moon, as a black disk with only such light behind and around it as may be reflected back onto the sky by the illuminated, but to the Earth invisible, hemisphere of the Moon, or as may proceed from the Sun's corona, to be described presently. The condition of things, therefore, is that known as a total eclipse of the Sun so far as regards the inhabitants of the narrow strip of Earth primarily affected. Figure 3 represents nearly, but not quite the same condition of things. Here the Earth and the Moon are in those parts of their respective orbits which put the two bodies at or near the maximum distance possible from the Sun and from one another. The Moon casts its usual shadow, but the tip does not actually reach any part of the Earth's surface. Or, in other words, to an observer on the Earth, the Moon is not big enough to conceal the whole body of the Sun. The result is this: at the instant of central coincidence, the Moon covers up only the center of the Sun, leaving the outer edge all round uncovered. This outer edge shows as a bright ring of light, and the eclipse is of the sort known as an annular eclipse of the Sun. As the greatest breadth of the annulus can never exceed 1½ minutes of arc, an annular eclipse may sometimes, in some part of its track, become almost or quite total, and vice versa. The idea will naturally suggest itself. What exactly does happen to the inhabitants living outside, on the one side or the other of the strip of the Earth where the central line of shadow falls? This depends, in every case, on circumstances. but it may be stated generally that the inhabitants outside the central line, but within 1,000 to 2,000 miles on either side, will see a larger or smaller part of the sun concealed by the moon's solid body, simultaneously with the total concealment of the sun to the favored individuals who live, or who for the moment are located within the limits of the central zone. Now we must advance one stage in our conceptions of the movements of the earth and the moon, so far as regards the bearing of those movements on the question of eclipses. The earth moves in a plane which is called the plane of the ecliptic, and correspondingly the sun has an apparent annual motion in the same plane. The moon, moving in a different plane, inclined to the first mentioned one to the extent of rather more than 5 degrees, the moon's orbit will evidently intersect the ecliptic in 2 places. These places of intersection are called nodes, and the line which may be imagined to join these nodes is called the line of nodes. When the moon is crossing the ecliptic from the south to the north side thereof, the moon is said to be passing through its ascending node. The converse of this will be the moon passing back again from the north side of the ecliptic to the south side, which is the descending node. Such changes of position, with the terms designating them, apply not only to the moon in its movement round the earth, but to all the planets and comets circulating round the sun, and also to satellites circulating round certain of the planets, but with these matters we have no concern now. End of Chapter 2. Recording by Linda Olson Fytak, Los Angeles.
Chapter 3 of The Story of Eclipses. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne Spiegel. The Story of Eclipses by George Chambers. Chapter 3. The Saros and the Periodicity of Eclipses. To bring about an eclipse of the sun, 2 things must combine. 1. The moon must be at or near one of its nodes, and 2. This must be at a time when the moon is also in conjunction with the sun. Now the moon is in conjunction with the sun, equals new moon, 12 or 13 times in a year, but the sun only passes through the nodes of the moon's orbit twice a year. Hence an eclipse of the sun does not and cannot occur at every new moon, but only occasionally. An exact coincidence of earth, moon, and sun in a straight line at a node is not necessary to ensure an eclipse of the sun. So long as the moon is within about 18½ degrees of its node, with a latitude of not more than 1 degree 34 minutes, an eclipse may take place. If, however, the distance is less than 15¼ degrees, and the latitude is less than 1 degree 23 minutes, an eclipse must take place, though between these limits the occurrence of an eclipse is uncertain and depends on what are called the horizontal parallaxes and the apparent semi-diameters of the 2 bodies at the moment of conjunction, in other words, on the nearness or far-offness of the bodies in question. Another complication is introduced into these matters by reason of the fact that the nodes of the moon's orbit do not occupy a fixed position, but have an annual retrograde motion of about 19¼ degrees, in virtue of which a complete revolution of the nodes round the ecliptic is accomplished in 18 years, 218 7/8 days, that is, 18.5997 years. The backward movement of the moon's nodes combined with the apparent motion of the sun in the ecliptic causes the moon, in its monthly course round the earth, to complete a revolution with respect to its nodes in a less time, 27.2 days, than it takes to get back to conjunction with the Sun, 29.5 days. And a curious consequence, as we shall see directly, flows from these facts, and from one other fact. The other fact is to the Sun's starting coincident with one of the Moon's nodes, returns on the ecliptic to the same node in 346.6 days. The first named period of 27.2 days is called the nodal revolution of the Moon, or Draconic month. The other period of 29.5 days is called the synodical revolution of the Moon. Now the curious consequence of these figures being what they are, is that 242 Draconic months, 223 lunations, and 19 returns of the Sun to one and the same node of the Moon's orbit are all accomplished in the same time within 11 hours. Thus, ignoring refinements of decimals, and here is a table: 242 times 27.2 days equals 6,585.36 days equals 18 years, 10 days, 8.5 hours. 223 times 29.5 days equals 6,585.32 days equals 18 years, 10 days, 7.75 hours. 19 times 346.6 days equals 6,585.78 days equals 18 years, 10 days, 18.75 hours. The interpretation to be put upon these coincidences is this: that supposing Sun and Moon to start together from a node, they would, after the lapse of 6,585 days and a fraction, be found again together very near the same node. During the interval there would have been 223 new and full moons. The exact time required for 223 lunations is such that in the case supposed, the 223rd conjunction of the two bodies would happen a little before they reached the node. Their distance therefrom would be 28 minutes of arc. And the final fact is that eclipses recur in almost, though not quite, the same regular order every 6,585 1/3 days, or more exactly, 18 years, 10 days, 7 hours, 42 minutes. This is the celebrated Chaldean Saros, and was used by the ancients, and can still be used by the moderns, in the way of a pastime, for the prediction of eclipses alike of the Sun and of the Moon. At the end of a Saros period, starting from any date that may have been chosen, the Moon will be in the same position with respect to the Sun, nearly in the same part of the heavens, nearly in the same part of its orbit, and very nearly indeed at the same distance from its node, as at the day chosen for the terminus a quo of the Saros. But there are trifling discrepancies in the case. The difference of about 11 hours between 223 lunations and 19 returns of the Sun to the Moon's node is 1. And these have an appreciable effect in disturbing not so much the sequence of the eclipses in the next following Saros, as their magnitude and visibility at given places on the Earth's surface. Hence, a more accurate succession will be obtained by combining 3 Saros periods, making 54 years 31 days, while, best of all, to secure an almost perfect repetition of a series of eclipses will be a combination of 48 Saroses, making 865 years for the Moon, and of about 70 Saroses, or more than 1,200 years for the Sun. These considerations are leading us rather too far afield. Let us return to a more simple condition of things. The practical use of the Saros in its most elementary conception is somewhat on this wise. Given 18 or 19 old almanacs ranging, say, from 1880 to 1898, how can we turn to account the information they afford us in order to obtain from them information respecting the eclipses which will happen between 1899 and 1917? Nothing easier. Add 18 years, 10 days, 7 hours, 42 minutes to the middle time of every eclipse which took place between 1880 and 1898, beginning, say, with the last of 1879 or the first of 1880, and we shall find what eclipses will happen in 1898 and the 17 following years, as witnessed by way of example the following table. Moon, magnitude 0.17. 1879, December 28th, 4 hours, 26 minutes p.m. Adding to that, 18 years, 10 days, 7 hours, 42 minutes, we get magnitude 0.16, 1898, January 8th, 12 hours, 8 minutes a.m. Error of Saros by exact calculation, civil time plus 3 minutes. Sun, total. 1880, January 11th, 10 hours, 48 minutes p.m. Adding to that, 18 years, 10 days, 7 hours, 42 minutes, we get total 1898, January 22nd, 6 hours, 30 minutes a.m. Error of Saros by exact calculation, civil time minus 1 hour, 7 minutes. Moon, magnitude total, 1880, June 22nd, 1 hour, 50 minutes p.m. Adding to that, 18 years, 11 days, 7 hours, 42 minutes, we get magnitude 0.93, 1898, July 3rd, 9 hours, 32 minutes p.m. Error of Saros by exact calculation, plus 35 minutes. Sun, magnitude annular, 1880, July 7th, 1 hour, 35 minutes p.m. Adding to that, 18 years, 11 days, 7 hours, 42 minutes, we get magnitude annular, 1898, July 18th, 9 hours, 17 minutes p.m. Error of Saros by exact calculation, plus 1 hour, 10 minutes. Sun, magnitude 0.04, 1880, December 2nd, 3 hours, 11 minutes a.m. civil time. Adding to that 18 years, 11 days, 7 hours, 42 minutes, we get magnitude 0.02, 1898, December 13th, 10 hours, 53 minutes a.m. Error of Saros by exact calculation, minus 1 hour, 5 minutes. Moon, magnitude total, 1880, December 16th, 3 hours, 39 minutes p.m. Adding to that, 18 years, 11 days, 7 hours, 42 minutes, we get magnitude total, 1898, December 27th, 11 hours, 21 minutes p.m. Error of Saros by exact calculation, minus 13 minutes. Sun, magnitude 0.71, 1880, December 31st, 1 hour, 45 minutes p.m. Adding to that, 18 years, 11 days, 7 hours, 42 minutes, we get magnitude 0.72, 1899, January 11th, 9 hours, 27 minutes p.m. Error of Saros by exact calculation, minus 1 hour, 11 minutes. There having been 5 recurrences of February 29th between December 1879 and January 1899, 5 leap years having intervened, we have to add an extra day to the Saros period in the latter part of the above table. Let us make another start and see what we can learn from the eclipses, say, of 1883. Moon, magnitude 0.8, 1883, April 22nd, 11 hours, 39 minutes a.m. Adding 18 years, 11 days, 7 hours, 42 minutes, we get Magnitude penumbral, 1901, May 3rd, 7 hours 21 minutes p.m. Error of Saros by exact calculation, plus 51 minutes. Sun, magnitude total, 1883, May 6th, 9 hours 45 minutes p.m. Visible Philippines. Adding 18 years, 11 days, 7 hours 42 minutes, we get magnitude total, 1901, May 18th, 5 hours 27 minutes a.m. Error of Saros by exact calculation, civil time, minus 2 minutes. Moon, magnitude 0.28, 1883, October 16th, 6 hours 54 minutes a.m. Visible California. Adding 18 years, 11 days, 7 hours and 42 minutes, we get magnitude 0.23, 1901, October 27th, 2 hours 36 minutes p.m. Error of Saros by exact calculation, minus 39 minutes. Sun, magnitude Annular, 1883, October 30th, 11 hours 37 minutes p.m. Visible Northern Japan. Adding 18 years, 11 days, 7 hours 42 minutes, we get magnitude Annular, 1901, November 11th, 7 hours 19 minutes a.m. Error of Saros by exact calculation, civil time plus 1 minute. The foregoing does not by any means exhaust all that can be said respecting the Saros, even on the popular side. If the Saros comprised an exact number of days, each eclipse of a second Saros series will be visible in the same regions of the earth as the corresponding eclipse in the previous series. But since there is a surplus fraction of nearly 1/3 of a day, each subsequent eclipse will be visible in another region of the earth, which will be roughly 1/3 of the earth's circumference in longitude backwards, i.e. about 120 degrees to the west, because the earth itself will be turned on its axis 1/3 forwards. After what has been said as to the Saros and its use, it might be supposed that a correct list of eclipses for 18.03 years would suffice for all ordinary purposes of eclipse prediction, and that the sequence of eclipses at any future time might be ascertained by adding to some one eclipse which had already happened so many Saros periods as might embrace the years future, whose eclipses it was desired to study. This would be true in a sense, but would not be literally and effectively true, because corresponding eclipses do not recur exactly under the same conditions, for there are small residual discrepancies in the times and circumstances affecting the real movements of the earth and moon and the apparent movement of the sun, which, in the lapse of years and centuries, accumulate sufficiently to dislocate what otherwise would be exact coincidences. Thus an eclipse of the moon, which in AD 565 was of 6 digits, was in 583 of 7 digits, and in 601 nearly 8. In 908 the eclipse became total and remained so for about 12 periods, or until 1088. This eclipse continued to diminish until the beginning of the 15th century, when it disappeared in 1413. Let us now take the life of an eclipse of the sun. One appeared at the North Pole in June A.D. 1295, and showed itself more and more towards the south at each subsequent period. On August 27, 1367, it made its first appearance in the north of Europe. In 1439 it was visible all over Europe. In 1601, being its 19th appearance, it was central and annular in England. On May 5, 1818, it was visible in London, and again on May 15, 1836. Its 3 next appearances were on May 26, 1854, June 6, 1872, and June 17, 1890. At its 39th appearance, on August 10, 1980, the moon's shadow will have passed the equator, and as the eclipse will take place nearly at midnight, Greenwich Mean Time, the phenomenon will be invisible in Europe, Africa, and Asia. At every succeeding period the central line of the eclipse will lie more and more to the south, until finally, on September 30th, 2665, which will be its 78th appearance, it will vanish at the South Pole. The operation of the Saros effects, which have been specified above, may be noticed in some of the groups of eclipses which have been much in evidence, as will appear from a subsequent chapter, during the second half of the 19th century. The following are two noteworthy Saros groups of solar eclipses: 1842, July 8th; 1860, July 18th; 1878, July 29th; 1896, August 9th; 1850, August 7th; 1868, August 17th; 1886, August 29th; 1904, September 9th. If the curious reader will trace, by means of the Nautical Almanac, or some other almanac which deals with eclipses in adequate detail, the geographical distribution of the foregoing eclipses on the Earth's surface, he will see that they fulfill the statement made on page 24, ante, that a Saros eclipse, when it reappears, does so in regions of the Earth averaging 120 degrees of longitude to the west of those in which it had, on the last preceding occasion, been seen, and also that it gradually works northwards or southwards. But a given Saros eclipse, in its successive reappearances, undergoes other transformations besides that of terrestrial longitude. These are well set forth by Professor Newcomb. Since every successive recurrence of such an eclipse throws the conjunction 28 minutes further to the west of the node, the conjunction must, in process of time, take place so far back from the node that no eclipse will occur, and the series will end. For the same reason there must be a commencement to the series, the first eclipse being east of the node. A new eclipse thus entering will at first be a very small one, but will be larger at every recurrence in each Saros. If it is an eclipse of the Moon, it will be total from its 13th until its 36th recurrence. There will then be about 13 partial eclipses, each of which will be smaller than the last, when they will fail entirely, the conjunction taking place so far from the node that the Moon does not touch the Earth's shadow. The whole interval of time over which a series of lunar eclipses thus extend will be about 48 periods, or 865 years. When a series of solar eclipses begins, the penumbra of the first will just graze the Earth not far from one of the poles. There will then be, on the average, 11 or 12 partial eclipses of the Sun, each larger than the preceding one, occurring at regular intervals of one Saros. Then the central line, whether it be that of a total or annular eclipse, will begin to touch the Earth, and we shall have a series of 40 or 50 central eclipses. The central line will strike near one pole in the first part of the series, in the equatorial regions about the middle of the series, and will leave the Earth by the other pole at the end. 10 or 12 partial eclipses will follow, and this particular series will cease. These facts deserve to be expanded a little. We have seen that all eclipses may be grouped into a series, and that 18 years or thereabouts is the duration of each series or Saros cycle. But these cycles are themselves subject to cycles, so that the Saros itself passes through a cycle of about 64 Saroses before the conditions under which any given start was made come quite round again. 64 times 18 makes 1152, so that the duration of a solar eclipse great cycle may be taken at about 1150 years. The progression of such a series across the face of the Earth is thus described by Mrs. Todd, who gives a very clear account of the matter. The advent of a slight partial eclipse near either pole of the Earth will herald the beginning of a new series. At each succeeding return, conformably to the Saros, the partial eclipse will move a little further towards the opposite pole, its magnitude gradually increasing for about 200 years. But during all this time only the lunar penumbra will impinge upon the Earth. But when the true shadow begins to touch, the obscuration will have become annular or total near the pole where it first appeared. the eclipse has now acquired a track, which will cross the Earth slightly farther from that pole every time it returns for about 750 years. At the conclusion of this interval, the shadow path will have reached the opposite pole. The eclipse will then become partial again, and continue to grow smaller and smaller for about 200 years additional. The series then ceases to exist, its entire duration having been about 1,150 years. The series of great eclipses, of which two occurred in 1865 and 1883, while others will happen in 1901, 1919, 1937, 1955, and again 1973, affords an excellent instance of the northward progression of eclipse tracks. And another series, with totality nearly as great, 1850, 1868, 1886, 1904, and 1922, is progressing slowly southwards. The word digit, formerly used in conjunction with eclipses, requires some explanation. The origin of the word is obvious enough, coming as it does from the Latin digitus, a finger. But as human beings have only 8 fingers and 2 thumbs, it is by no means clear how the word came to be used for twelfths of the disk of the sun or moon instead of tenths. However, such was the case. And when a 16th century astronomer spoke of an eclipse of 6 digits, he meant that 1/2 of the luminary in question, be it sun or moon, was covered. The earliest use of the word digit in this connection was to refer to the 12th part of the visible surface of the sun or moon. But before the word went out of use, it came to be applied to 12ths of the visible diameter of the disk of the sun or moon, which was much more convenient. However, the word is now almost obsolete in both senses, and partial eclipses, alike of the sun and of the moon, are defined in decimal parts of the diameter of the luminary, tenths or hundredths, according to the amount of precision which is aimed at. Where an eclipse of the moon is described as being of more than 12 digits, or more than 1.0 equals 1 diameter, it is to be understood that the eclipse will be, or was, not only total, but that the moon will be, or was, immersed in the Earth's shadow, with a more or less considerable extent of shadow encompassing it. There are some further matters which require to be mentioned connected with the periodicity of eclipses. To use a phrase which is often employed, there is such a thing as an eclipse season, and what this is can only be adequately comprehended by looking through a catalogue of eclipses for a number of years arranged in tabular form, and by collating the months or groups of months in which batches of eclipses occur. This is not an obvious matter to the casual purchaser of an almanac, who, feeling just a slight interest in the eclipses of a coming year, dips into his new purchase to see what those eclipses will be. A haphazard glance at the almanacs of even 2 or 3 successive years will probably fail to bring home to him the idea that each year has its own eclipse season, in which eclipses may occur, and that eclipses are not to be looked for save at 2 special epochs, which last about a month each, and which are separated from one another and from the eclipse season of the previous and the following years by intervals of about 6 months, within a few days, more or less. Such, however, is the case. A little thought will soon make it clear why such should be the case. We have already seen that the moon's orbit, like that of every other planetary member of the solar system, has 2 crossing places with respect to the ecliptic, which are called nodes. We know also that the apparent motion of the sun causes that body to traverse the whole of the ecliptic in the course of the year. The conjoint result of all this is that the moon passes through a node twice in every lunar month of 27 days, and the sun passes, apparently, through a node twice in every year. The first ultimate result of these facts is that eclipses can only take place at or near the nodal passages of the moon and the sun, and that as the sun's nodal passages are separated by 6 months in every case, the average interval between each set of eclipses, if there is more than one, must in all cases be 6 months, more or less by a few days, dependent upon the latitude and longitude of the moon at or about the time of its conjunction or opposition under the circumstances already detailed. If the logic of this commends itself to the reader's mind, he will see at once why eclipses or groups of eclipses must be separated by intervals of about half an ordinary year. Hence it comes about that, taking one year with another, it may be said that we shall always have a couple of principal eclipses with an interval of half a year, say 183 days, between each, and that on either side of these dominant eclipses there will, or may be, a fortnight before or fortnight after, two other pairs of eclipses with, in occasional years, one extra thrown in. It is in this way that we obtain what has already been said dogmatically that we do obtain, namely, always in 1 year 2 eclipses, which must both be of the Sun, or any number of eclipses up to 7, which number will be unequally allotted to the Sun or to the Moon according to circumstances. Though it is roughly correct to say that the 2 eclipse seasons of every year run to about a month each, in length, yet it may be desirable to be a little more precise, and to say that the limits of time for solar eclipses cover 36 days, namely 18 days before and 18 days after the Sun's nodal passages, whilst in the case of the Moon the limits are the lesser intervals of 23 days, being 11½ on either side of the Moon's nodal passages. We have already seen that the Moon's nodes are perpetually undergoing a change of place. Were it not so, eclipses of the Sun and Moon would always happen year after year in the same pair of months for us on the Earth. But the operative effect of the shifting of the nodes is to displace backwards the eclipse seasons by about 20 days. For instance, in 1899 the eclipse seasons fall in June and December. The middle of the eclipse seasons for the next succeeding 20 or 30 years will be found by taking the dates of June 8th and December 2nd, 1899, and working the months backwards by the amount of 19 2/3 days for each succeeding year. Thus the eclipse seasons in 1900 will fall in the months of May and November. Accordingly, amongst the eclipses of that year we shall find eclipses on May 28th, June 13th, and November 22nd. Perhaps it would tend to the more complete elucidation of the facts stated in the last half-dozen pages, if I were to set out in a tabular form all the eclipses of a succession, say a half of a Saros or 9 years, and thus exhibit by an appeal to the eye directly the grouping of eclipse seasons, the principles of which I have been endeavoring to define and explain in words. And here follows a table, with this explanation. The epochs in the last column which are marked with stars, star or double star as the case may be, represent corresponding nodes, so that from any one singular star date to the next nearest single star date means an interval of 1 year less, on an average, the 19 2/3 days spoken of on page 32. A glance at each successive pair of dates will quickly disclose the periodical retrogradation of the eclipse epochs. And then reading the table. 1894, March 21st, lunar. April 6th, solar. Epoch, March 29th, star. September 15th, lunar. September 29th, solar. Epoch, September 22nd, double star. 1895, March 11th, lunar. March 26th, solar. Epoch, March 18th, star. August 20th, solar. September 4th, lunar. September 18th, solar. Epoch, September 4th, double star. 1896, February 13th, solar. February 28th, lunar. Epoch, February 20th, star. August 9th, solar. August 23rd, lunar. Epoch, August 16th, double star. 1897, February 1st, solar. Epoch, February 1st, star. July 29th, solar. Epoch, July 29th, double star. 1898, January 7th, lunar. January 22nd, solar. Epic. January 14th, star. July 3rd, lunar. July 18th, solar. Epic. July 10th, double star. December 13th, solar. December 27th, lunar, and 1889, January 11th, solar. Epic. December 27th, star. Continuing 1899, June 8th, solar. June 23rd, lunar. Epic. June 15th, double star. December 2nd, solar. December 16th, lunar. Epic. December 9th, star. 1900. May 28th, solar. June 13th, lunar. Epic. June 5th, double star. November 22nd, solar. Epic. November 22nd, star. 1901. May 3rd, lunar. May 18th, solar. Epic. May 10th, double star. October 27th, lunar. November 11th, solar. Epic. November 3rd, star. 1902. April 8th, solar. April 22nd, lunar. May 7th, solar. Epic. April 22nd, double star. And October 17th, lunar. October 31st, solar. Epic. October 24th, star. End of Chapter 3.
Chapter 4 of the Story of Eclipses. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Andrea Kay. The Story of Eclipses by George Chambers. Chapter 4. Miscellaneous theoretical matters connected with eclipses of the sun chiefly. One or two miscellaneous matters respecting eclipses of the sun chiefly will be dealt with in this chapter. It is not easy to explain or define in words the circumstances which control the duration of a solar eclipse, whereas in the case of a lunar eclipse, the obscuration is the same in degree at all parts of the earth where the moon is visible. In the case of a solar eclipse, it may be total, perhaps, in Africa, may be of 6 digits only in Spain, and of 2 only in England. Under the most favorable circumstances, the breadth of the track of totality across the earth cannot be more than 170 miles, and it may be anything less than that down to 0, where the eclipse will cease to be total at all and will become annular. The question whether a given eclipse shall exhibit itself on its central line as a total or an annular one depends, as has been already explained, on the varying distances of the Earth and the Moon from the Sun in different parts of their respective orbits. Hence it follows that not only may an eclipse show itself for several Saros appearances as total, and afterwards become annular, and vice versa, but on rare occasions one and the same eclipse may be annular in one part of its track across the Earth, and total in another part a short time earlier or later. This last named condition might arise because the Moon's distance from the Earth or the Sun had varied sufficiently during the progress of the eclipse to bring about such a result, or because the shadow just reaching the Earth and no more, the eclipse would be total only for the moment when a view perpendicular upwards could be had of it, and would be annular for the minutes preceding and the minutes following the perpendicular glimpse obtained by observers actually on the central line. The eclipse of December 12, 1890 was an instance of this. If the paths of several central eclipses of the Sun are compared by placing side by side a series of charts, such as those given in the Nautical Almanac or in Oppolzer's Canon, it will be noticed that the direction of the central line varies with the season of the year. In the month of March, the line runs from southwest to northeast, and in September from northwest to southeast. In June, the line is a curve, going first to the northeast and then to the southeast. In December, the state of things is reversed, the curve going first to the southeast and then to the northeast. At all places within about 2,000 miles of the central line, the eclipse will be visible. And the nearer a place is to the central line, so much the larger will be the portion of the sun's disk concealed from observers there by the moon. If the central line runs but a little to the north of the equator in winter, or of 25 degrees of north latitude in summer, the eclipse will be visible all over the northern hemisphere, and the converse will apply to the southern hemisphere. It is something like a general rule in the case of total and annular eclipses, though subject to many modifications, that places within 200 to 250 miles of the central line will have partial eclipse of 11 digits, from thence to 500 miles of 10 digits, and so on, diminishing something like 1 digit for every 250 miles, so that at 2,000 miles, or rather more, the sun will be only to a very slight extent eclipsed, or will escape eclipse altogether. The diameter of the sun being 866,000 miles, and the moon being only 2,160 miles, or 1/400th, how comes it to be possible that such a tiny object should be capable of concealing a globe 400 times bigger than itself? The answer is distance. The increased distance does it. The moon at its normal distance from the Earth of 237,000 miles could only conceal by eclipse a body of its own size or smaller. But the sun being 93 million miles away, or 392 times the distance of the moon, the fraction 1/392, representing the main distance of the moon, more than wipes out the fraction 1/400, which represents our satellite's smaller size. During a total eclipse of the sun, the moon's shadow travels across the Earth at a prodigious pace, 1,830 miles an hour, 30.5 miles a minute, or rather more than a half mile a second. This great velocity is at once a clue to the fact that the total phase during an eclipse of the sun lasts for so brief a time as a few minutes, and also to the fact that the shadow comes and goes almost without being seen unless a very sharp watch is kept for it. Indeed, it is only observers posted on high ground with some miles of open low ground spread out under their eyes who have much chance of detecting the shadow come up, go over them, and pass forwards. Places at or near the Earth's equator enjoy the best opportunities for seeing total eclipses of the sun, because whilst the moon's shadow travels eastwards along the Earth's surface at something like 2,000 miles an hour, an observer at the equator is carried in the same direction by virtue of the Earth's axial rotation at the rate of 1,040 miles an hour. But the speed imparted to an observer as the result of the Earth's axial rotation diminishes from the equator towards the poles, where it is nil, so that the nearer he is to a pole, the slower he goes, and therefore the sooner will the moon's shadow overtake and pass him, and the less the time at his disposal for seeing the sun hidden by the moon. It was calculated by du Séjour that the greatest possible duration of the total phase of a solar eclipse at the equator would be 7 minutes 58 seconds, and for the latitude of Paris, 6 minutes 10 seconds. In the case of an annular eclipse, the figures would be 12 minutes 24 seconds for the equator, and 9 minutes 56 seconds for the latitude of Paris. These figures contemplate a combination of all the most favorable circumstances possible. As a matter of fact, I believe that the greatest length of total phase which has been actually known was 6.5 minutes, and that was in the case of the eclipse of August 29, 1886. It was in the open Atlantic that this duration occurred, but it was not observed. The maximum observed obscuration during this eclipse was no more than 4 minutes. Though total eclipses of the Sun happen with tolerable frequency so far as regards the Earth as a whole, yet they are exceedingly rare at any given place. Take London, for instance. From the calculations of Hind, confirmed by Weir, it may be considered as an established fact that there was no total eclipse visible at London between AD 878 and 1715, an interval of 837 years. The next one visible at London, though uncertain, is also a very long way off. There will be a total eclipse on August 11, 1999, which will come as near to London as the Isle of Wight. But Hind, writing in 1871, said that he doubted whether there would be any other total eclipse visible in England for 250 years from the present time. Weir states that the Sun has been eclipsed, besides twice at London, also twice at Dublin, and no fewer than 5 times at Edinburgh during the 846 years examined by him. In fact, that every part of the British Isles has seen a total eclipse at some time or other between AD 878 and 1724, except a small tract of country at Dingle on the west coast of Ireland. The longest totality was on June 15, 885, namely 4 minutes 55 seconds, and the shortest in July 16, 1330, namely 0 minutes 56 seconds. Contrast with this the obscure island of Blanquilla, off the northern coast of Venezuela. The inhabitants of that island not long ago had the choice of 2 total eclipses within 3.5 years, namely August 29, 1886 and December 22, 1889, whilst Yellowstone, U.S. had 2 in 12 years, July 29, 1878 and January 1, 1889. Counting from first to last, Dussaiger found that at the equator an eclipse of the Sun might last 4 hours 29 minutes, and at the latitude of Paris 3 hours 26 minutes. These intervals, of course, cover all the subordinate phases. The total phase, which alone, with perhaps a couple of minutes added, is productive of spectacular effects and interesting scientific results, is a mere matter of minutes, which may be as few as 1 or less, or only as many as 6 or 8. As a rule, a summer eclipse will last longer than a winter one, because in summer, the Earth and the Moon with it, being at its maximum distance from the Sun will be at its minimum apparent size, and therefore the Moon will be able to conceal it the longer. End of Chapter 4. Recording by Andrea K.
Chapter 5 of The Story of Eclipses. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne Spiegel. The Story of Eclipses by George Chambers. Chapter 5. What is observed during the earlier stages of an eclipse of the Sun. The information given in this and the next following chapters will almost exclusively concern total and annular eclipses of the Sun, for, in real truth, there's practically only one thing to think about during a partial eclipse of the Sun. This is, to watch when the Moon's black body comes on to the Sun and goes off again, for there are no subsidiary phenomena, either interesting or uninteresting, unless, indeed, the eclipse should be nearly total. The progress of astronomical science in regard to eclipses has been so extensive and remarkable of late years that, unless the various points for consideration are kept together under well-defined heads, it will be almost impossible either for a writer or a reader to do full justice to the subject. Having regard to the fact that the original conception of this volume was that it should serve as a forerunner to the total solar eclipse of May 28, 1900, and through that to other total eclipses. From a popular rather than from a technical standpoint, I think it would be best to mention one by one the principal features which spectators should look out for, and to do so as nearly as may be in the order which nature itself will observe when the time comes. Of course, the commencement of an eclipse, which is virtually the moment when the encroachment on the circular outline of the sun by the moon begins, or can be seen, though interesting as a proof that the astronomer's prophecy is about to be fulfilled, is not a matter of any special importance, even in a popular sense, much less in a scientific sense. As a rule, the total phase does not become imminent, so to speak, until a whole hour and more has elapsed since the first contact, and that hour will be employed by the scientific observer less in looking at the sun than in looking at his instruments and apparatus. He will do this for the purpose of making quite sure that everything will be ready for the total utilization to the utmost extent of the precious seconds of time into which all his delicate observations have to be squeezed during the total phase. With these preliminary observations, I shall proceed now to break up the remainder of what I have to say respecting total eclipses into what suggest themselves as convenient sectional heads. The moon's shadow and the darkness it causes. In awaiting the darkness which is expected to manifest itself, an unthinking and inexperienced observer is apt to look out for the coming obscurity, as he looks out for nightfall half an hour or more after sunset and during the evening twilight. The darkness of an eclipse is all this and something more. It is something more in two senses. For the interval of time between the commencement of an eclipse and totality is different in duration and different in quality, so to speak, from the diminution of daylight on the earth, which ensues as the twilight of evening runs its course. Speaking roughly, sunset may be described as an almost instantaneous loss of full sunlight, and the gradual loss of daylight is noticeable even at such short intervals as from 5 minutes to another. This is by no means the case previous to a total eclipse of the sun. When that is about to occur, the reduction of the effective sunlight is far more gradual. For instance, half an hour after an eclipse has commenced, more than half the sun's disk will still be imparting light to the earth, but half an hour after the sunset, the deficiency of daylight will be very much more marked and, if no artificial light is at hand, very much more inconvenient. If there should be within easy reach of the observer's post a bushy tree, such for instance as an elm 30 feet or 40 feet high, and spreading out sufficiently for him to place himself under it in a straight line with the sun, and with a nice smooth surface of ground for the sun's rays to fall on, he will see a multitude of images of the sun thrown upon the ground. Until the eclipse has commenced, these images will be tiny circles overlapping one another, and of course, each of these circles means so many images of the sun. These images indeed can be seen on any fine day, and the circles increase in size in proportion to the height of the foliage above the ground, being something like 1 inch for every 10 feet. It may be remarked, by the way, that the images are circles because the sun is a source of light having a circular outline, and is not a point of light like a star. If it were, the outline of the foliage would be reproduced on the ground leaf for leaf. It follows naturally from all this that when in consequence of there being an eclipse in progress, the shape of the sun's contour gradually changes, so will the shape of the solar images on the ground change, becoming eventually so many crescents. Moreover, the horns of the crescent-shaped images will be in the reverse direction to the horns of the actual crescent of the sun at the moment, the rays of the sun crossing as they pass through the foliage, just as if each interstice were a lens. Supposing there are some spots on the sun at a time when an eclipse is in progress, the moon's passage over those spots may as well be noticed. In bygone years some amount of attention was devoted to this matter, with the view of ascertaining whether any alteration took place in the appearance of the spots, distortion, for instance, such as might be produced by the intervention of a lunar atmosphere. No such distortion was ever noticed, and observations with this idea in view may be said to possess now only an academic interest, for it may be regarded as a well-established fact that the moon has no atmosphere. During the passage of the moon over sunspots, an opportunity is afforded of comparing the blackness, or perhaps we should rather say, the intensity of the shade of a sunspot with the blackness of the moon's disk. Testimony herein is unanimous that the blackness of the moon during the stages of a partial eclipse is intense compared with the darkest parts of a sunspot, and this, be it remembered, in spite of the fact that during the partial phase the atmosphere between the observer and the sun is brilliantly illuminated, whilst the moon itself, being exposed to earthshine, is by no means absolutely devoid of an illumination. When the moon is passing across the sun, there have often been noticed along the limb of the moon fringes of color and dark and bright bands. This might not necessarily be a real appearance, for it is conceivable that such traces of color might be due to the telescopes employed not having been truly achromatic, that is, not sufficiently corrected for color. But making every allowance for this possible source of mistake, there yet remains proof that the color which has often been seen has been real. As to whether the moon's limb can be seen during a partial eclipse, or during the partial phase of what is to be a total eclipse, the evidence is somewhat conflicting. There is no doubt that when the totality is close at hand, the moon's limb can be seen projected on the corona, presently to be described. But the question is, whether the far-off limb of the moon can be detected in the open sky, whilst something like full daylight still prevails on earth. Undoubtedly, the preponderance of evidence is against the visibility of the moon as a whole under such circumstances, but there is nevertheless some testimony to the contrary. A French observer, Elie, said that 3 photographic plates of the eclipse of 1858, seen in South America, all showed the outer limb of the moon with more or less distinctness. This testimony, be it noted, is photographic and not visual, and on the whole it seems safest to say that there is very small probability of the moon as a whole ever being seen under the circumstances in question. What has just been said concerns the visibility of the moon during quite the early, or on the other hand during quite the late, stages of the total eclipse. Immediately before or after totality, the visibility of the whole contour of the moon is a certain fact, and the only point upon which there is a difference of opinion is as to what are the time limits beyond which the moon must not be expected to be seen. The various records are exceedingly contradictory. Perhaps the utmost that can be said is that the whole moon must not be expected to be visible until about 20 minutes before totality, or for more than 5 minutes after totality, but it must be admitted that these figures are very uncertain in regard to any particular eclipse. It has been sometimes noticed, when the crescent of the sun has become comparatively small, say that the sun was about 7/8 covered, that the uncovered portion exhibited evident color which has been described variously as violet, brick red, reddish, pink, orange, yellowish. The observations on this point are not very numerous and, as will appear from the statement just made, are not very consistent. Still, it seems safe to assume that a hue, more or less reddish, does often pervade the uncovered portion of a partially eclipsed sun. The remark just made as regards the sun seems to have some application to the moon. There are a certain number of instances on record that what is commonly spoken of as the black body of the moon does, under certain circumstances, display traces of red, which has been variously spoken of as crimson, dull coppery, reddish brown, and dull glowing coal. Shadow bands. Let us suppose that we have a chance of observing a total eclipse of the sun, have completed all our preliminary preparations, have taken note of everything which needs to be noted or suggests itself for the purpose up till nearly the grand climax, and that the clock tells us that we are within, say, 5 minutes of totality. Somewhere about this time, perhaps, we shall be able to detect, dancing across the landscape, singular wavy lines of light and shade. These are the shadow bands, as they are called. The phrase is curiously inexplicit, but seemingly cannot be improved upon at present because the philosophy of these appearances, their origin and the laws which regulate their visibility, are unknown, perhaps because amid the multitude of other things to think about sufficient attention has hitherto not been paid to the study of them. These shadow bands are most striking if a high plastered wall, such as the front of a stone or stuccoed house, is in their track as a screen to receive them. The shadow bands seem to vary both in breadth and distance apart at different eclipses, and also in the speed with which they pass along. Though, as already stated, little is known of their origin, yet they may be conceived to be due to irregularities in the atmospheric refraction of the slender beam of light coming from the waning or waxing crescent of the sun, For be it understood, they may be visible after totality as well as before it. It is to be remarked that they have never been photographed. In addition to the shadow bands, there are instances on record of the limbs of the sun's crescent appearing to undulate violently on the approach of totality. These undulations were noticed by Airy in 1842, about 6 minutes before totality. Blake, in America in 1869, observed the same phenomenon 8 minutes before totality. In other cases the interval would seem to have been very much shorter, a mere matter of seconds. A very singular observation was made in 1858 by Mr. J. D. Smith at Laycock Abbey, Wiltshire, on the occasion of the annular eclipse of that year. He says, "Both my brother and myself were distinctly impressed with the conviction that the withdrawal of light was not continuous, but by pulsations, or, as it were, waves of obscuration, the darkness increasing by strokes which sensibly smote the eye, and were repeated distinctly some 5 or 7 times after we had remarked the phenomenon, and before the time of greatest obscuration. They did not occur on the return of light, which came back continuously and without shock or break." Rümker mentions that though this phenomenon was very apparent to the naked eye, it was not visible in the telescope. Faint rays or brushes of light sometimes seem to spring from the diminishing crescent of the sun. These rays generally are very transient and are not very conspicuous, and perhaps must be distinguished as regards both their appearance and their origin from the more striking rays which are usually seen a few minutes before or after totality, and which are generally associated with, or even deemed to belong to, the corona. Fig. 7 represents these rays as seen in Spain on July 18, 1860, some minutes after totality. They are described as having been well defined, but at some moments more marked than at others, and though well defined, yet constantly varying. Radiations of light, more or less of the character just described, may probably be regarded as a standing feature of every total eclipse. The approach of totality. The next thing to think about and to look for is the approach of the moon's shadow. I have mentioned this already, and also the appalling velocity with which it seems to approach. By this time the coming darkness, which characterizes every total phase, will have reached an advanced stage of development. The darkness begins to be felt. The events which manifest themselves at this juncture on the earth, rather than in the sky around the sun, are so graphically described by the American writer whom I have already quoted, and who writes, moreover, from personal experience, that I cannot do better than transfer her striking account to my pages. Then, with frightful velocity, the actual shadow of the moon is often seen approaching, a tangible darkness advancing almost like a wall, swift as imagination, silent as doom. The immensity of nature never comes quite so near as then, and strong must be the nerves not to quiver as this blue-black shadow rushes upon the spectator with incredible speed. A vast, palpable presence seems overwhelming in the world. The blue sky changes to gray or dull purple, speedily becoming more dusky, and a death-like trance seizes upon everything earthly. Birds with terrified cries fly bewildered for a moment, and then silently seek their night quarters. Bats emerge stealthily. Sensitive flowers, the scarlet pimpernel, the African mimosa, close their delicate petals, and a sense of hushed expectancy deepens with the darkness. An assembled crowd is awed into absolute silence almost invariably. Trivial chatter and senseless joking cease. Sometimes the shadow engulfs the observer smoothly, sometimes apparently with jerks, but all the world might well be dead and cold and turned to ashes. Often the very air seems to hold its breath for sympathy, and at other times a lull suddenly awakens into a strange wind, blowing with unnatural effect. Then out upon the darkness, gruesome but sublime, flashes the glory of the incomparable corona, a silvery, soft, unearthly light, with radiant streamers, stretching at times millions of uncomprehended miles into space, while the rosy, flaming protuberances skirt the black rim of the moon in ethereal splendor. It becomes curiously cold. Dew frequently forms, and the chill is perhaps mental as well as physical. Suddenly, instantaneous as a lightning flash, an arrow of actual sunlight strikes the landscape, and earth comes to life again, while the corona and protuberances melt into the returning brilliance, and occasionally the receding lunar shadow is glimpsed as it flies away with the tremendous speed of its approach. In connection with the approach of the moon's shadow, it is to be noted that at totality the heavens appear in a certain sense to descend upon the earth. If an observer is looking upwards towards the zenith over his head, he will see the clouds appear to drop towards the earth, and the surrounding gloom seems also to have the effect of vitiating one's estimate of distances. To an observer upon a high hill, a plain below him appears to become more distant, although what has been called the descent of the clouds, that is to say, their appearance of growing proximity, is most manifest immediately before the totality, yet a sense of growing nearness may sometimes be noticed a very considerable time before the total phase is reached. Whilst on the subject of clouds, it may be mentioned that although there is in the vault of heaven generally during the total phase an appreciable sensation of black darkness, more or less absolute, that is to say, either blackish or grayish, yet in certain regions of the sky, generally in the direction of the horizon, the clouds, where there are any, often exhibit colors in strata, orange hue below and red above, with indigo or gray or black higher up still, right away to the sun's place. The cause of these differences is to be found in the fact that the lower part of the atmosphere within the area of the moon's shadow is, under the circumstances in question, illuminated by light which, having passed through many miles of atmosphere near to the earth's surface, has lost much from the violet end of its spectrum, leaving an undue proportion of the red end. On certain occasions iridescent or rainbow-tinted clouds may be seen in the vicinity of the sun, either before or during or after totality, depending on circumstances unknown. Such clouds have been observed at all these three stages of a total eclipse. The effects, of course, are atmospheric, and have no physical connection with either sun or moon. The darkness of totality. With respect to the general darkness which prevails during totality, greater discrepancies appear in the accounts, not only as between different eclipses, but in respect of the same eclipse observed by different people at different places. Perhaps the commonest test applied by most observers is that of the facility or difficulty of reading the faces of chronometers or watches. Sometimes this is done readily, at other times with difficulty. In India, in 1868, one observer stated that it was impossible to recognize a person's face 3 yards off, and lamplight was needed for reading his chronometer. On the other hand, in Spain in 1860, it was noted that a thermometer, as well as the finest handwriting, could be read easily. The foregoing remarks apply to the state of things in the open air. In 1860, it was stated that inside a house in Spain the darkness was so great that people moving about had to take great care lest they should run violently against the household furniture. Perhaps on the whole it may be said that the darkness of an ordinary totality is decidedly greater than that of a full moon night. Many observers have noted during totality that even when there has not been any very extreme amount of absolute darkness, yet the ruddy light already mentioned as prevailing towards the horizon often gives rise to weird, unearthly effects, so that the faces of bystanders assume a sickly, livid hue, not unlike that which results from the light of burning salt. Meteorological and other effects. It is very generally noticed that great changes take place in the meteorological conditions of the atmosphere as an eclipse of the sun runs its course from partial phase to totality, and back again to partial phase. It goes without saying that the obstruction of the solar rays by the oncoming moon would necessarily lead to a steady and considerable diminution in the general temperature of the air. This has often been made the matter of exact thermometric record, but it is not equally obvious why marked changes in the wind should take place. As the partial phase proceeds, it is very usual for the wind to rise or blow in gusts and to die away during totality, though there are many exceptions to this, and it can hardly be called a rule. The depression of temperature varies very much indeed according to the locality where the eclipse is being observed, and the local thermometric conditions which usually prevail. The actual depression will often amount to 10 degrees to 20 degrees, and the deposit of dew is occasionally noticed. In addition to the general effects of a total solar eclipse on men, animals, and plants, as summarized in the extract already made from Mrs. Todd's book, A few additional particulars may be culled from many recorded observations. Flowers and leaves which ordinarily close at night begin long before totality to show signs of closing up. Thus we are told that in 1836 the crocus, gentian, and anemone partially closed their flowers and reopened them as the phenomenon passed off, and a delicate South African mimosa, which we had reared from a seed, entirely folded its pinnate leaves until the sun was uncovered. In 1851 the night violet, which shortly before the beginning of the eclipse had little of its agreeable scent about it, smelt strongly during the totality. In the insect world, ants have been noticed to go on working during totality, whilst grasshoppers are still by the darkness, and earthworms come to the surface. Birds of all kinds seem always upset in their habits, almost invariably going to roost as the darkness becomes intensified before totality. In 1868 a small cock, which had beforehand been actively employed in grubbing about in the sand, went to sleep with his head under his wing and slept for about 10 minutes, and on waking uttered an expression of surprise, but did not crow. In 1869 mention is made of an unruly cow, accustomed to jump into a cornfield at night, being found to have trespassed into the said cornfield during the total phase. The thrilling descriptions of the effects of the oncoming darkness of totality, derived from the records of past total eclipses, are not likely to be improved upon in the future, for we shall receive them more and more from amateurs and less from astronomical experts. Every additional total eclipse which happens testifies to the fact that the time and thoughts of those later classes of people will be to an increasing degree dedicated to instrumental work rather than to simple naked eye or even telescopic observation. The spectroscope and the camera are steadily ousting the simple telescope of every sort and unassisted eye observations from solar eclipse work. Mrs. Todd has the following apt remarks by way of a summary of the results to an individual observing a total eclipse of the sun. I doubt if the effect of witnessing a total eclipse ever quite passes away. The impression is singularly vivid and quieting for days, and can never be wholly lost. A startling nearness to the gigantic forces of nature and their inconceivable operation seems to have been established. Personalities and towns and cities, and hates and jealousies, and even mundane hopes, grow very small and very far away. End of chapter 5. Chapter 6 of The Story of Eclipses. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Story of Eclipses by George Chambers. Chapter 6. What is observed during the total phase of an eclipse of the sun? The central feature of every total eclipse of the sun is undoubtedly the corona, and the phenomena connected with it. But immediately before the extinction of the sun's light, and incidental thereto, there are some minor features which must be briefly noticed. The corona first makes its appearance on the side of the dark moon opposite to the disappearing crescent, but brushes of light are sometimes observed on the same side along the convex limb of the disappearing crescent. The appearance of the brushes will be sufficiently realized by an inspection of the annexed engraving without the necessity of any further verbal description. These brushes are little, if at all, colored, and must not be confused with the red flames or prominences hereafter to be described. Baily's Beads. When the disk of the moon has advanced so much over that of the sun as to have reduced the sun almost to the narrowest possible crescent of light, it is generally noticed that at a certain stage the crescent suddenly breaks up into a succession of spots of light. These spots are sometimes spoken of as rounded spots, but it is very doubtful whether, certainly in view of their supposed cause, they could possibly be deemed ever to possess an outline, which by any stretch could be called rounded. Collating the recorded descriptions, some such phrase as shapeless beads of light would seem to be the most suitable designation. These are observed to form before the total phase, and often also after the total phase has passed. Under the latter circumstances, the beads of light eventually run into one another, like so many small drops of water merging into one big one. The commonly received explanation of Baily's beads is that they are no more than portions of the sun's disk, seen through the valleys between the mountains of the moon, the said mountains being the cause why the bright patches are discontinuous. It is exceedingly doubtful whether this is the true explanation. The whole question is involved in great uncertainty, and well deserves careful study during future eclipses. But this it is not likely to get, in view of the current fashion of every sufficiently skilled observer concentrating his attention on matters connected with the solar corona, observed spectroscopically or otherwise, to the exclusion of what may be called older subjects of study. I will dismiss Baily's beads from our consideration with the remark that the first photograph of them was obtained at Ottumwa, Illinois, U.S., during the eclipse of 1869. Baily's beads received their name from Mr. Francis Baily, who in 1836 for the first time exhaustively described them, but they were probably seen and even mentioned long before his time. At the total eclipse of the Sun, seen at Penobscot in North America on October 27, 1780, they would seem to have been noticed, and perhaps even earlier than that date. Almost coincident with the appearance of Baily's beads, that is, either just before or just after, and also just before or just after the absolute totality, there seems no certain rule of time, jets of red flame are seen to dart out from behind the disk of the moon. It is now quite recognized as a certain fact that these red flames belong to the sun, and are outbursts of hydrogen gas. Moreover, they are now commonly called prominences, and with the improved methods of modern science may be seen almost at any time when the sun is suitably approached, and they are not restricted in their appearance to the time when the sun is totally eclipsed, as was long supposed. I may have more to say about these red flames later on, but am at present dealing only with the outward appearances of things. Carrington's description has been considered very apt. One which he saw in 1851 he likened to a mighty flame bursting through the roof of a house and blown by a strong wind. Certain ambiguous phrases made use of in connection with eclipses of ancient date may perhaps in reality have been allusions to the red flames. Otherwise the first account of them given with anywhere like scientific precision seems to be due to a Captain Stannyan, who observed them at Bern during the eclipse of 1706. His words are that the sun at his getting out of his eclipse was preceded by a blood-red streak from his left limb, which continued not longer than 6 or 7 seconds of time. Then part of the sun's disk appeared all of a sudden. Some subsequent observers spoke of the red flames as isolated jets of red light appearing here and there, whilst others seem to have thought they had seen an almost or quite continuous ring of red light around the sun. The last named idea is now recognized as the more accurate representation of the actual facts, the red flames being emanations proceeding from a sort of shell enveloping the sun, to which shell the name of chromosphere has now come to be applied. As regards the moon itself during the continuance of a total phase, all that need be said is, that our satellite usually exhibits a disk which is simply black, but on occasions observers have called it purplish or purple. Although during totality the moon is illuminated by a full allowance of earthshine, light reflected by the earth into space, yet from all accounts this is always insufficient to reveal any traces of the irregularities of mountains and valleys, etc., which exist on the moon. When during totality any of the brighter planets, such as Mercury, Venus, Mars, Jupiter, or Saturn, happen to be in the vicinity of the sun, they are generally recognized, but the stars seen are usually very few, and they are only very bright ones of the first or second magnitudes. Perhaps an explanation of the paucity of stars noticed is to be found in the fact that the minds of observers are usually too much concentrated on the sun and moon for any thought to be given to other things or other parts of the sky. Perhaps this is a convenient place in which to recall the fact that there has been much controversy in the astronomical world during the last 50 years as to whether there exist any undiscovered planets revolving around the sun within the orbit of Mercury. Whilst there is some evidence, though slight, that one or more such planets have been seen, opponents of the idea base their skepticism on the fact that with so many total eclipses as there have been since 1859, when Lescarbault claimed to have found a planet which had been called Vulcan, no certain proof has been obtained of the existence of such a planet, and what better occasion for finding one, if one exists of any size, than the darkness of a total solar eclipse. At present it must be confessed that the skeptics have the best of it. The corona. We now have to consider what I have already called the central feature of every total eclipse. It was long ago compared to the nimbus often placed by painters around the heads of the Virgin Mary and other saints of old, and as conveying a rough general idea, the comparison may still stand. It has been suggested that not a bad idea of it may be obtained by looking at a full moon through a wire gauze window screen. The corona comes into view a short time, usually to be measured by seconds, before the total extinction of the sun's rays, lasts during totality and endures for a brief interval of seconds, or it might be a minute, after the sun has reappeared. It was long a matter of discussion whether the corona belonged to the sun or the moon. In the early days of telescopic astronomy there was something to be said perhaps on both sides, but it is now a matter of absolute certainty that it belongs to the sun, and that the moon contributes nothing to the spectacle of a total eclipse of the sun except its own solid body, which blocks out the sun's light, and its shadow, which passes across the earth. Of the general appearance of the corona some idea may be obtained from Figure 1, which so far as it goes needs little or no verbal description. Stress must, however, be laid on the word general, because every corona may be said to differ from its immediate predecessor and successor, although, as we shall see presently, there is strong reason to believe that there is a periodicity in connection with coronas, as with so many other things in the world of astronomy. A curious point may here be mentioned as apparently well established, namely, that when long rays are noticed in the corona, they do not seem to radiate from the sun's center as the short rays, more or less, seem to do. Though the aggregate brilliancy of the corona varies somewhat, yet it may be taken to be much about equal on the whole to the moon at its full. The corona is quite unlike the moon as regards heat, for its radiant heat has been found to be very well marked. There is another thing connected with the sun's corona which needs to be mentioned at the outset, and which also furnishes a reason for treating it in a somewhat special manner. The usual practice in writing about science is to deal with it in the first instance descriptively, and then, if any historical information is to be given, to exhibit that separately and subsequently. But our knowledge of the sun's corona has developed so entirely by steps from a small beginning that it is neither easy nor advantageous to keep the history separate or in the background, and I shall therefore not attempt to do so. Astronomers are not agreed as to what is the first record of the corona. It is commonly associated with a total eclipse which occurred in the 1st century A.D., and possibly in the year 96 A.D. Some details of the discussion will be found in a later chapter, and I will make no further allusion to the matter here. Passing over the eclipses of 968 A.D. and 1030 A.D., the records of both of which possibly imply that the corona was noticed, we may find ourselves on thoroughly firm ground in considering the eclipse of April 9, 1567. Clavius, a well-known writer on chronology, undoubtedly saw then the corona in the modern acceptation of the word, but thought it merely the uncovered rim of the sun. In reply to this, Kepler showed by some computations of his own, based on the relative apparent sizes of the sun and moon, that Clavius's theory was untenable. Kepler, however, put forth a theory of his own, which was no better, namely, that the corona was due to the existence of an atmosphere round the moon, and proved its existence. From this time forwards we have statements by various observers, applying to various eclipses, of the corona seeming to be endued with a rotatory motion. The Spanish observer, Don A. Ulloa, in 1778, wrote thus respecting the corona seen in that year: "After the immersion, we began to observe round the moon a very brilliant circle of light, which seemed to have a rapid circular motion something similar to that of a rocket turning about its center." Modern observations furnish no counterpart of these ideas of motion in the corona. Passing over many intervening eclipses, we must note that of 1836, which gave us Baily's Beads, as the first which set men thinking that total eclipses of the sun exhibited subsidiary phenomena deserving of careful and patient attention. Such attention was given on the occasion of the eclipses of 1842 and 1851, still, however, without the corona attracting that interest which it has gained for itself more recently. It was noticed, indeed, that the corona always first showed itself on the side of the Moon farthest from the vanishing crescent, but the full significance of this fact was not at first realized. Mrs. Todd well remarks, "In the early observations of the corona it was regarded as a halo merely and so drawn. Its real structure was neither known, depicted, nor investigated. The earliest pictures all show this. Preconceived ideas prejudiced the observers and their sketches were mostly structureless. It should not be forgotten that the coronal rays project outward into space from a spherical sun, and do not lie in a plane as they appear to the eye in photographs and drawings." After remarking on the value of photographs of the corona up to a certain point, because of their automatic accuracy, Mrs. Todd very sensibly says, "But pencil drawings, while ordinarily less trustworthy because involving the uncertain element of personal equation, are more valuable in delineating the finest and faintest detail of which the sensitive plate rarely takes note. The vast array of both, however, shows marked differences in the structure and form of the corona from one eclipse to another, though it has not yet revealed rapid changes during any one observation." This last interesting feature can only be studied by comparison of photographs near the beginning of an eclipse track and its end, 2 or 3 hours of absolute time apart. Concerted efforts to accomplish this were made in 1871, 1887, and 1889, but they broke down because the weather failed at one or the other end of the chain of observing stations, and a succession of photographs, not simultaneous but separated by sufficient intervals of time, could not be had. The eclipse of 1893, however, yielded successful though negative results. Photographs in South America compared with photographs in Africa 2 hours later in time disclosed no appreciable difference in the structure of the corona and its streamers. The eclipse of May 28, 1900, will furnish the next favorable opportunity for a repetition of this experiment, by reason of the fact that the line of totality begins in North America, crosses Portugal and Spain, and ceases in Africa. In other words, traverses countries eminently calculated to facilitate the establishment of photographic observing stations, where observations can be made not simultaneously but at successive intervals spread over several hours. Although of course the corona had been observed long before the year 1851, as indeed we have already seen, yet the eclipse of 1851 is the farthest back which we can safely take as a starting point for gathering up thoroughly precise details, because it was the first at which photography was brought into use. Starting, therefore, with the eclipse, I want to lay before the reader some of the very interesting and remarkable generalisms which, thanks especially to Mr. W. H. Wesley's skillful review of many of the photographic results, are now gradually unfolding themselves to astronomers. To put the matter in the fewest possible words, there seems little or no doubt that according as spots on the sun are abundant or scarce, so the corona, when visible during an eclipse, varies in appearance from one period of 11 years to another like period. Or, to put it in another way, given the date of a coming total eclipse, we can predict to a certain extent the probable shape and character of the corona, if we know how the forthcoming date stands as regards a sunspot maximum or minimum. The most recent important eclipses up to date which have been observed, namely those of April 16, 1893, August 9, 1896, and January 21, 1898, do not add much to our useful records of the outward appearances presented by the corona. The 1896 corona is described as intermediate between the two types respectively associated with years of maximum and minimum sunspots. And this is as it should have been, albeit there was one extension which reached to about 2 diameters of the sun. The 1898 corona yielded 4 long coronal streamers, reaching much farther from the sun than any previously seen, the 2 longest reaching to 4½ and 6 diameters of the sun respectively. These dimensions are quite unprecedented. The application of the spectroscope to observations of eclipses of the sun demands a few words of notice in this place, but it would not be consistent with the plan of this work to go into details. Though the spectroscope has been applied under many different circumstances to different parts of the sun's surroundings in connection with total eclipses, yet it is in regard to the corona that most has been done and most has been discovered. The substance of the discoveries made is that the corona shines with an intrinsic light of its own. That is to say, that it is composed of constituents whose temperature is sufficiently elevated to be self-luminous. These constituents are chiefly hydrogen, the body of which corresponds to the line D3 on Fraunhofer's scale, and which has been named helium, and the body which corresponds to the bright green line 1474 of Kirchhoff's scale, and which, since its existence was first suspected and then assured, has been named coronium. The reader will not be surprised to learn, from what has gone before, that an immense mass of records have accumulated respecting the appearance of the corona. Correspondingly numerous and divergent are the theories which have been launched to explain the observations made. One thing is in the highest degree probable, namely, that electricity is largely concerned. Going back to the question of sunspots, regarded in their possible or probable association with the corona, the present position of matters appears to be this: that there is a real connection between the general form of the corona and disturbances on the Sun, taking sunspots as an indication of solar activity. When sunspots are at or near their maximum, the corona has generally been somewhat symmetrical, with synclinal groups of rays making angles of 45 degrees with its general axis. On the other hand, at the epochs of minimum sunspots, the corona shows polar rifts much more widely open, with synclinal zones making larger angles with the axis, and being, therefore, more depressed towards the equatorial regions, in which, moreover, there is usually a very marked extension of coronal matter in the form of elongated streamers reaching to several diameters of the Sun. This generalization is well borne out by the maximum epoch coronas of 1870 and 1871, and the minimum epoch coronas of 1867, 1874, 1875, 1878, and perhaps 1887, and certainly 1889. On the other hand, the eclipses of 1883, 1885, and 1886 do not strikingly confirm this theory. The eclipse of 1883 was at a time of rapidly decreasing solar activity, yet the corona had the features of a sunspot maximum. The same, though in a somewhat less degree, may be said of the eclipses of 1885 and 1886. At the times of both of these eclipses the solar activity was decreasing. The forthcoming eclipse of 1900 will nearly coincide with a sunspot minimum, and if the above conclusions are well founded, the corona in 1900 should resemble that of 1889, and be characterized by, amongst other things, some very elongated groups of rays extending in nearly opposite directions. We are still a long way off from being able to state with perfect confidence what the corona is. It is certainly a complex phenomenon, and the various streamers which we see are not, as was at one time imagined, a simple manifestation of one radiant light. Mrs. Todd thus conveniently summarizes the present state of our knowledge. The true corona appears to be a triple phenomenon. First, there are the polar rays, nearly straight throughout their visible extent. Gradually, as these rays start out from points on the solar disk farther and farther removed from the poles, they acquire increasing curvature, and very probably extend into the equatorial regions, but are with great difficulty traceable there, because projected upon and confused with the filaments having their origin remote from the poles. Then there is the inner equatorial corona, apparently connected intimately with truly solar phenomena, quite like the polar rays, while the third element in the composite is the outer equatorial corona, made up of the long elliptic streamers, for the most part visible only to the naked eye, also existing as a solar appendage and possibly merging into zodiacal light. The total eclipses of half a century have cleared up a few obscurities and added many perplexities. There is little or no doubt about the substantial, if not entire, reality of the corona as a truly solar phenomenon. The Moon, if it has anything at all to do with the corona, aside from the fact of its coming inconveniently between Sun and Earth, so as to allow a brief glimpse of something startlingly beautiful which otherwise could never have been known, is probably responsible for only a very narrow ring of the inner radiance of pretty even breadth all around. This diffraction effect is accepted, but the problem still remains how wide this annulus may be, and whether it may vary in width from one eclipse to another. These questions once settled, the spurious structure may then be excerpted from the true. Indeed, the coronal streamers, delicately curving and interlacing, may tell the whole story of the sun's radiant energy. End of chapter 6. Chapter 7 of The Story of Eclipses. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Story of Eclipses by George Chambers. Chapter 7. What is observed after the total phase of an eclipse is at an end. In a certain sense, a description of the incidents which precede the total disappearance of the sun in connection with the total eclipse will apply more or less to the second half of the phenomenon, only, of course, in the reverse order and on the opposite side of the compass. The corona having appeared first of all on the west side of the sun, and then having shown itself complete as surrounding the sun, will begin to disappear on the west side, and will last be seen on the east side. Baily's beads may or may not come into view. The sun will reappear first as a very thin crescent, gradually widening. The quasi-nocturnal darkness visible on earth will cease, and eventually the moon will completely pass away from off the sun, and the sun once again will exhibit a perfect circle of light. Whilst there is so much to look for and look at and think about, one thing must be sought for instantly after totality, or it will be gone forever, and that is the moon's shadow on the earth. We have already seen in the last chapter the startling rapidity and solemnity with which the shadow seems to rush forward to the observer from the horizon on the western side of the meridian. Passing over him, or even, so to speak, through him, it travels onward in an easterly direction, and very soon vanishes. Its visibility at all depends a good deal upon whether the observer, who is looking for it, is sufficiently raised above the adjacent country to be able to command at least a mile or two of ground. If he is in a hollow, he will have but little chance of seeing the shadow at all. On the other hand, if he is on the top of a considerable hill, or high up on the side of a hill, commanding the horizon for a distance of 10 or 20 miles, he will have a fair chance of seeing the shadow. Sir G. B. Airy states in 1851, "My eye was caught by a duskiness in the southeast, and I immediately perceived that it was the eclipse shadow in the air, traveling away in the direction of the shadow's path. For at least 6 seconds this shadow remained in sight, far more conspicuous to the eye than I had anticipated. I was once caught in a very violent hail and thunderstorm on the tableland of the country of Sutherland called the Moyne, and I at length saw the storm travel away over the North Sea, and this view of the receding eclipse shadow, though by no means so dark, reminded me strongly of the receding storm. In 10 or 12 seconds all appearance of the shadow had passed away." Perhaps this may be a convenient place to make note of what seems to be a fact, partly established at any rate, that there seems some connection between eclipses of the sun and earthquakes. A German physicist named Ginzel has found a score of coincidences between solar eclipses and earthquakes in California in the years between 1850 and 1888 inclusive. Of course there were eclipses without earthquakes and earthquakes without eclipses, but 20 coincidences in 38 years seems suggestive of something. End of chapter 7.